Welcome to the Building Better Batteries webinar series that is sponsored by Thermo Fisher Scientific. My name is Christina Pogel, Senior Manager at Wiley for Content Strategy, and it is a pleasure to open the last part of our 8-part webinar series that explores the intricate process of battery development from materials research to cell manufacturing. This series aims to identify the unmet needs and prevent failures while maintaining high-quality assurance standards. You will learn about essential topics that ensure the quality and longevity of batteries, gaining insights into advanced techniques and methodologies by diagnosing battery issues, understanding failure root causes, and implementing preventive strategies.
As a company, Thermo Fisher Scientific has a clear mission: to enable our customers to make the world healthier, cleaner, and safer. Let's break that down a bit further. Healthier. Thermo Fisher Scientific contributes to human health by empowering our customers with advanced technologies and expertise. This allows them to develop breakthrough medicines and diagnostics that improve lives across the globe. From life-saving treatments to innovative diagnostics, our customers rely on us to help them achieve the impossible. Cleaner. In the fight against climate change and environmental degradation, Thermo Fisher Scientific provides the tools to understand these challenges and develop greener solutions. Our technologies help ensure the quality of air and water, essential elements for life on our planet. Together with our customers, we are committed to preserving the environment for future generations. Safer. From detecting contaminants in food to solving crimes and identifying threats, we help our customers protect their communities. Our instruments and solutions are designed to keep people safe, and together, we are determined to make the world a safer place. At Thermo Fisher Scientific, we are not just creating products. We're enabling our customers to make an impact on the world. Thermo Fisher Scientific is the global leader in serving science operating in 170 territories with over 140,000 colleagues, generating over $40 billion of revenue, and they reinvesting almost $1.3 billion annually in new products. Within the battery market, Thermo Fisher Scientific partners globally to deliver advanced integrated solutions from the research laboratory to the battery production line that ensure material quality and accelerate improvements in battery production efficiency. Thermo Fisher Scientific serves the battery value chain with advanced analytics from research to recycling, with market-leading technologies in spectroscopy, electron microscopy, and mass spectrometry. Within this webinar series, we will be focusing on the mining and mineral processing, battery component materials QC, and production pieces of the battery manufacturing value chain. There are many dynamics affecting the battery industry. Firstly, to compete in the battery marketplace, new battery manufacturers need to get to high yield, high volume manufacturing fast. Poor quality costs material, production volume, and time. We must prioritize quality. Saving money on metrology is seldom rewarded with anything but headaches. Companies are prioritizing quality. Secondly, new battery companies are investing in innovation. There's little chance to catch up with established battery manufacturing companies in China by repeating what they do. Companies are looking to leapfrog. They are investing in advanced technologies early to facilitate faster product development and troubleshooting of quality failures. Thirdly, new battery companies are thinking globally. They may have a laboratory and pilot line in Mumbai, but they will want to replicate that capability as they scale their operations in Europe and North America. Consequently, they need global partners who can support their growth in every territory.
And now I'll hand over to Jay, who will moderate this panel discussion.
So hi, everyone. My name is Jay Anye. I'm a Senior Business Development Manager at Thermo Fisher Scientific. And thank you all for joining today's discussion on the challenges for next-generation battery technologies. So this discussion is going to focus on bringing together researchers from academia and battery industry experts to explore the future of battery technology. The discussion will focus on the roadmap for next-generation battery technologies and that promise higher energy density, faster charging times, greater safety, and improve sustainability. So our panelists will delve into the latest advancements in different battery technology. And as a listener, you'll gain valuable insight into the strategic roadmap that's needed to drive innovation and meet our growing global battery demand. So thank you all again for joining. Now I will turn it over to our speakers to kind of give a brief introduction. So Shirley, would you like to introduce yourself?
Hi, everyone. I'm Shirley Meng, professor from the University of Chicago, Pritzker School of Molecular Engineering. I also serve as the chief scientist for Argonne National Laboratories, Energy Storage Science.
Wonderful. Glad to have you here, Shirley. And Yury?
Hi, I'm Yury Gogotsi. I'm a professor of material science and engineering at Drexel University in Philadelphia. And I also serve as a director of the Drexel Nanomaterials Institute.
Wonderful. Glad to have you here, Professor Yury. And Kang?
Good morning, everyone. My name is Kang Zu. Currently, I'm serving as CTO of SES AI, which is a startup company working to develop the advanced lithium-metal batteries. Before I joined the company, I worked in government lab for over 26 years. Our laboratory under DoD. I work on electrolytes and interfaces.
Wonderful. Thank you for joining us, Kang. So let's go ahead and get started. The first question I have for this team here is, why do you believe we need new battery technology? So what do you see as the most pressing unmet need in our current battery technology that the next generation batteries should aim to address? And Shirley, I'll start with you.
All right. I'll kick off the discussions. I just mentioned maybe a couple important points regarding battery technologies. Lead acid batteries has been with us for over 150 years, lithium-ion batteries over 30 years. These are the only two technologies that reached 1 terawatt hour per year capacity so far. But according to a lot of us projection for truly enable energy transition with renewables and low carbon sources, the whole world probably will need up to 200 to 300 terawatt hour batteries in total. So there's a huge gap in terms of what humanity needs and what currently the battery technologies are. I think that will be the first big drivers that why we need new battery technologies. The second important fact I want to share with everyone is that battery safety has been significantly improved over the last 30 years. Today, lithium-ion battery community ship out over 1 billion cells every year, even though the accident still happens, but please remember it's less than 1 in 10 million in terms of the failure rates, but still that has caused a lot of worries among the people. So we have to do better. The scientists are always up for the challenge. So that's why in concerning the safety aspect of the lithium-ion batteries, current status, I think a lot of us are working on new technology, new battery technologies that can provide the high energies not without compromise the safety. So I think these two, for me, the bigger drivers for keeping me, up every day to work on batteries.
Well said. Safety is most important. So thank you for that. And then Yury, same question to you.
We need also diverse batteries, because whether we're talking about automotive or personal electronics, or the future Internet of Things, wearable technology, powering billions of sensors that will monitor our health and environment around us, or about high energy density batteries for drones or electric planes, or very large scale energy storage that Shirley mentioned for grid storage. We need different kinds of batteries with very different materials. And addressing each of those challenges is important. So we need to widen the spectrum of available energy storage sources. And for some devices, for example, like flying objects, gravimetric energy density is the key. But for personal electronics, Internet of Things devices, it may be the volumetric. We want to have the tiniest, smallest batteries. And there are many applications where we need very high cycle life. We won't be able to ever replace a battery. And where we also need different shapes, structural batteries eventually. So I think this is where new materials will play a key role.
Right. Yeah, that's a really good point. Thank you, Professor Yury. Kang, go to you.
I am completely in agreement with what my colleagues are saying. So one thing I want to point out is that lithium-ion battery was invented by a series of technical monuments starting in 1972 and finally commercialized in 1991. So the entire process took 20 years. And once it's commercialized and made available to the public, because the ongoing electrification revolution, which is still affecting every aspect of our life. So currently, as we are entering the new age of every country around the world concerned with energy security and the independence, computing powers resources are rapidly speeding up and reshaping our world. We can only imagine that what new energy or what new battery materials can make a difference in the future, in our energy future. And in this case, we think that we still in the huge demand of energy gap, which the current lithium-ion battery chemistry cannot provide, because constrained by the intrinsic limits imposed by the interconnection chemistry, they cannot, for example, drive the electroflights or such as the commercial airliners. We have to find out what new battery chemistries can bring us to the.
Very good point, Kang. Okay, and then the next question I have for you, Professor Shirley, maybe if you'd like to start. So, how do you envision future battery technology to evolve over the next decade? And I guess specifically in your research, what role does your research play in this evolution?
So I am a trained material scientist. So our contributions to the future battery technologies are really from the atomic and the molecular level up. The whole battery technology take the entire group of scientists, engineers to develop. But what we envision, I will now wear the hat as the director of the Energy Storage Research Alliance, ESRA, the newly launched Department of Energy Basic Energy Science under the hub. Here we are really looking at alternative chemistry, such as sodium batteries, organic flow batteries, or even metal air batteries. What we envision for the future battery technology is really hinges on the ability to further lower the cost by enabling materials that are much more abundant and could be locally sourced and produced. I think that what we see, the production of the lithium-ion batteries currently are not well balanced in terms of where those materials are being mined, processed, and produced. So hopefully our research currently at a pretty low technology readiness level will enable a more I would say, democratized way of how we look at battery technologies and secure the supply chains, particularly for the North America and Europe regions. I think my own research, for instance, I'm a material scientist. I utilize a lot of advanced characterization tools such as cryo transmission electron microscopy, synchrotron, which Argonne National Lab is hosting one of the world's most brilliant and coherent X-ray source. It's important to realize that at a molecular level, we can control matter to the precision where energy storage, when you do the device, you can precisely control where working ions like lithium, sodium, maybe in the future will be potassium or other elements, that where they go and how we suppress all parasitic reactions in the batteries through this kind of discoveries enabled by the advanced characterization. So yeah, the key enabler for me, from my perspective, is really the breakthroughs in new materials discovery, advanced tools that can enable us to see what naked eyes cannot see. Only after we build an extremely strong foundation from the science, then we can move towards engineering, where, of course, we'll rely on industrial partners to enable translating those science into impactful technologies.
Yeah, well said. And speaking of industrial partners, I guess I'd like to maybe move over to you, Kang, and get your perspective on that, and how you envision the future of battery technology to evolve, and how you're involved in that evolution.
In my perspective from industry manufacturing, I would think that the material chemistry constitutes a basic foundation for any future chemistry of battery, which can be put in practical use. As Shirley pointed out, the entire history of human developing or using battery of 200 years, slightly more than 200 years, there are only two rechargeable battery chemistries which really penetrated our life, because each battery consists of different components, and all these components have to be well synchronized in order to make the whole device work. In the past, where the invention of battery technology has been based on the coincidental serendipity discoveries, not entirely driven by the rational design. And we think that for the next battery, for the future of the energy storage technology, we have to invest more in understanding not only the basic science, but also how to leverage the current huge database we are building and rationally design based on the firm scientific understanding. So currently, what I'm working on is we are trying to leverage the ongoing AI machine learning revolution to design new materials, new molecules for the next battery chemistry. And my specialized area is electrolytes. In our survey, we found that in the past 30 years, since lithium battery invention, there are only about over slightly more than hundreds of chemicals, unique chemicals used in the research, and very few of those really mean a product. We want to change that. On the other hand, the large uncharted molecular universe is huge, on the order of 10 to the 11th or 10 to the 20th of magnitude, depending on how you confine the universe. We believe that in those vast unexplored universe, there's one ideal, and it's the one ideal electrolyte or electrolyte material which can enable us to make the future ideal battery.
Very good. Yeah, the electrolyte is very key for battery technology. So thank you, Kang. And then same question to you, Yury. Do you have anything you'd like to add?
Well, what I would like to add to this, that in my opinion, again, batteries will evolve into a variety of dimensions, sizes, and chemistries. We will have micro batteries to power all our Internet of Things devices. We will also have, I'm a believer into metal sulfur batteries, lithium sulfur, sodium sulfur batteries, utilizing abundant sodium, not using any critical elements. And I think this will also be a significant part of the future energy landscape. I think those are the future battery technologies that will be growing and developing. In particular, we discovered a very large family of two-dimensional materials, carbides and nitrides, called MXenes. And many of them, like titanium carbide MXenes, are made of abundant elements and have much higher conductivity compared to reducing graphene oxide, other carbon materials used, which can provide high rate performance, which can minimize resistive losses of batteries, especially compensating for low conductivity of sulfur, also providing flexibility in printable, flexible, wearable devices. So, similar to Professor Shirley Meng, I'm a material scientist, and we discover and develop new materials for applications in electrochemical energy storage.
Wonderful. Thank you. Yeah. And then, so going back to you, Shirley, you know, given the future of battery technology, what do you see as the current focus? Is it going to be solid state or lithium ion? And you mentioned even sodium ion. And then, what are your predictions for the future of battery manufacturing based on these technologies? I'd love to get your thoughts.
Yep. So I think when we talk about all these new battery technologies, people try to categorize solid versus liquid, lithium metal, sodium. But I want to emphasize the solid and the liquid is referring to the electrolyte. Lithium metal is the negative electrode, so they don't contradict to each other. So bottom line is that on the roadmap for battery community, we have several promising technologies that can lead to a few exciting breakthroughs in the battery technologies. The reason we pursue solid state is because there is a possibility to enable very high energy density cells without compromise safety. So lithium metal can be the anode, sodium metal can be the anode. So it's a versatile technology platform. So I personally am very excited about the potential for solid state batteries. We also have the potential to revolutionize liquid electrolytes. So typical liquid electrolytes use, carbonate or ether-based electrolytes, but there's a lot more molecules out there that can potentially lead to batteries that can enable fast charging, more powerful batteries. So, in terms of the manufacturing, I think the most exciting aspect for me is really to think about how battery manufacturing can be further simplified. So dry electrode processing is one of those process that can enable simplification of battery manufacturing process. So current, the steps towards preparing for the next generation batteries is really for us to think about, okay, the first couple of terawatt hour done. In the future, how can we innovate in the battery manufacturing space to further break down bring down the cost, and then to enable new chemistry. Think about how it's like, Lego play for the manufacturing. How can you modify the factories that you can do liquid lithium metal, and then perhaps another line next to it, you can do solid state lithium metal. So those are the, in our vision, our planning, all are still on the discussion board because we are only 2 or 3% into making all the batteries that humanity need for energy transition. So I hope we will be able to attract a lot of young, talented people to come in and join us to think about what future manufacturing could look like. How can we leverage AI, machine learning, and automations to really revolutionize how manufacturing jobs look like in the future. So I personally am excited, really excited about those future directions.
Yeah. Excellent. And I just wanted to follow up on one of the comments you made about, AI and machine learning. Is that something that your team is actively using as you plan out these new battery technologies?
So we are fundamental researchers. Okay, so our focus is really the AI for materials discovery and science. Yes, we are already, so in the ESRA, the newly launched energy storage hub, AI accelerated materials discovery is one of the key crosscut that help us to, for instance, one of our scientific trust is called soft matter omics. We have a concerted effort to bring in the top researchers in the world to think about how organic materials can also participate in active energy storage. When we talk about organic molecules, the space for exploration is vast. So how can we actually quickly narrow down the candidates? Yeah, there we will be able to utilize quite a lot of the machine learning tools to help a scientist to narrow down the list where we are going to experimentally explore those materials. And we call it omics because in the biological field, the word omics is used quite often. Really, it is a data-driven, how to build a database and utilize database and have the, because it's a multi-dimensional optimization process. We have to heavily rely on machine learning tools for helping be a co-pilot with the scientist to think about how can we design the next soft matter, you can call it a polymeric materials, not only doing electrolyte work, but actually being able to store and convert electrons reversibly. And for us, this is a very exciting, new emerging area that Esra will be focusing on. So yeah, I will leave the manufacturing jobs to our industry colleagues.
Yeah, very fascinating. Thank you, Shirley. And then I'll pass it over to you, Yury. So, given the future of the battery technology, where do you see the current focus from your perspective? Is it the solid state or lithium metal? And similar on the manufacturing side, if you have any comments.
I first think many different kind of batteries, as I already mentioned, will play a role in the future. Yeah, solid state technology is clearly promising, has been promising for a while, but for example, the fundamental issue of solid state diffusion probably won't allow us to have really high power, fast batteries. One technology that has not been mentioned today yet is aqueous batteries. For example, zinc metal batteries, zinc ion batteries, again, utilizing both safe electrolytes and also abundant elements like zinc, will also be and are already a focus of research. And I think the role of such technologies, not utilizing toxic electrolytes, utilizing abundant elements, carbon, zinc, will be increased. Regarding the manufacturing, I firmly believe that in the future, many things will change. Today, pretty much every battery is a kind of a scroll. We have a foil. Technology has been developed over decades and is being used. Is this the best one? Can we just prepare from a slurry, layer by layer, active material, current collector, separators in a much cheaper way, again, without using lots of organic solvents? I think those are all opportunities for the future. And we have lots of manufacturing processes like a 3D printing and others that can be used to print batteries where it's needed. So I think those are changes that will come necessarily in the future, again, diversifying the way we manufacture and use batteries for different applications.
Yeah, well said. And just to follow up there, so you mentioned zinc metal batteries. I'm curious, maybe you can briefly touch on some of the challenges of zinc metal batteries.
Well, zinc batteries have been used for a long time as primary batteries, and reversibility is a challenge. And the same dendrites that create a challenge for lithium metal batteries are challenging for zinc. So, overcoming dendrites, finding right electrolytes, coatings, those are same fundamental issues that battery community deals with. And we're trying to use our materials to suppress dendrite growth like MAXINs. And I think this is one of the key challenges, reversibility. We're also looking for example, like chloride electrolytes, which are very aggressive, and use of metal current collectors is a challenge. But again, we have now materials like titanium carbide MAXINs that can work in chloride electrolytes. So I think we need lots of components to be redesigned, change new materials to make technologies which we know are feasible, really practical and working and become scalable, reliable, and satisfy our need for energy storage.
I see. Thank you. Yeah. And then, going to our industry expert over here, Kang, um, in your perspective, where do you see the current focus from the industry? Is it, so I hear a lot about sodium ion. Is it that or solid state or what are your thoughts on the current focus?
Well, if you look at the periodic table, you would know that the most powerful anode was already given by God or by Big Bang. That's lithium. So in my perspective, in the future, the most powerful battery, no matter what cathode materials you use, no matter what electrolyte you use, lithium has to be a part of it. That's for the most powerful battery, I'm saying. But then like Yury mentioned that for diverse applications, you need diverse batteries. You don't need to have the highest energy density for every application. For example, these small microsensors, Internet of Things, or stationary grid storage application purposes. They don't require them much high gravimetric energy density. They require safety. They require very extra long cycle life or calendar life. Require very low cost and earth abundant elements. So from my perspective, I work primarily focus on the liquid and semi-liquid, semi-solid, I would say, electrolyte batteries. Versus Shirley. Shirley has been expanding her expertise in all three phases, to my knowledge so far: gas, solid, and liquid as well. So, in my perspective, I think that AI and machine learning will play a huge critical role in the future of it. Not only is the material discovery, molecular design, but also in safety and manufacturing. That's what our company is doing right now. We emphasize a lot of developing, investing a lot of resources to develop the models which can predict the safety issues of any battery, hundreds cycles before that even that happens, or applying AI technology which controls quality, controlling each individual cell from its birth from material all the way into the working cycle, for example, in a UV. So AI, especially in recent years, the rapidly developing graphic processing units, GPU, give us a lot of power to apply and develop those models. But to make those models reliable, we need huge data sets. And one big efforts I'm leading as a company, not only in my company, but also in the non-profit entity we set up, a molecular universe, is trying to raise the public awareness and leverage the public resource to explore the uncharted molecular universe in order to tap the huge uncharted molecular universe for the betterment of human being with the energy future.
Thank you, Kang. Wonderful. All right. And so the next question I have for you, specifically for you, Shirley, in terms of characterization, since I know your research involves a lot of characterization, given your expertise, what are some limitations of the current methods in analyzing battery materials? And what do you think, how can these be addressed?
Mhm. Yeah, Jay, I think it's a really important question for all the people who are working in the characterization side of the research area. So energy storage and conversion devices often operate at energetic state of the materials, right? That's why we can convert energy and store energy. So that make a lot of these materials are actually quite sensitive towards the environment. For instance, in the case of lithium metal reacts with everything. At the room temperature, it reacts with reacts with nitrogen, reacts with oxygen, reacts with CO2. And, in the last few years, one of the most significant progress on the characterization side is we have been able to significantly slow down the reactivity of the lithium metal or sodium metal or many alkaline metals through cryogenic techniques. So that is a tool that we pioneer in my group and together with many other top researchers in the world, we really see a tool we borrowed from biology side. Actually, I should say, cryo-EM really started from materials people, not bio side. But they made a better use of the tool and developed it further. So I think that this kind of cryogenic tools are very important for the future of energy materials, not just for batteries, but for catalysis, for MOF, COF, CO2 and the methane storage and the capture. I think that we're really seeing an era of how material scientists and the biologists, not only for this omic, database building, but also think about how characterization methods can be more robust, more reliable, and more reproducible and contributing to the database that we are hoping to establish. So I think the limitation really is that unlike the biofield, we don't have a very good agreement about the curation of the data. And that really needs to be resolved when we actually utilizing more imaging tools like cryo-EM, and in the future, I think a synchrotron computed tomography will be a very important tool when we look at the solid state batteries, because all the interfaces are buried. In liquid electrolyte and the gaseous electrolyte, you can let the electrolyte evaporate and then observe the interface. But in the solid state, the interfaces are all buried, and then you can't really detach these interfaces. So to see those interfaces requires a brand new way of thinking about how to do sample preparation, how to review the buried interfaces. So that requires the sample transfer in a very controlled environment, a clean way to go from large scale observation to atomic level scale observations. So I think the limitations there is we're going to see really the needs for having certain workflow sample prep that can enable us to study these buried interfaces in its pristine state or in its excited states. Yeah, so operando experiment with those buried interfaces also very exciting, challenging. So analyzing these battery materials, the goal is to really capture those all parasitic reactions so that I can propose solutions or propose to the industrial colleagues. Here is where is the problem is. It's very much like how doctor by the disease, you need, breast cancer, you need the kind of advanced characterization tools to know where is the cancer cell, so then you can have a targeted treatment. So I think moving forward for the battery, the cell format is becoming larger or become miniature, to the two extreme ends. And we need the characterization tools to really perform what doctors for batteries that we will be able to capture and give diagnosis in a very accurate, very reliable way, so that our industry colleagues can immediately, very quickly come out with mitigation strategies.
Yeah, well said. Challenge accepted. Thank you, Shirley. What do you believe are the most pressing challenges related to electrolytes and the next generation batteries? And how do you suggest we tackle some of those challenges?
Like we discussed a few minutes ago, that the needs for batteries are diverse, and there are huge diversity of battery chemistries. So each battery has its own requirement or demanding requirement for electrolytes. For the ultimate anode materials, lithium, Shirley just mentioned that lithium is very powerful, but its disadvantage is also it's too powerful. It reacts with everything, and the interface of lithium with any electrolyte material is a key. So that is the one area we haven't fully understood, and the atomic and molecular level from a science perspective. So far right now is that we have rough relation between the molecular structure of the electrolytes or even the electrolyte formulation liquid structure level to the final property, which was empowered by the ACI, or which is short for solid electrode interface. But we haven't built up the firm scientific foundation in order to precisely design ACI. So for the future battery chemistry, the one key tool we would need is the advanced in situ non-invasive characterization techniques, which can allow us to directly see the ACI, the growth, the evolution, and the failure of the ACI. That is one critical issue there. And again, on this, we are also trying to apply the leverage AI technique. Often we have thousands of SEM, TM pictures. We took those pictures, but we have very limited manpower to annotate the data, to analyze the picture. And AI here can really help us.
Yeah, absolutely. Thank you, Kang. And then this, last question goes to you, Yury. How do these materials compare to traditional battery materials? And what are some unique challenges they present? When we talk about these nanomaterials and other compounds that your research involves.
Well, first, carbon materials have been used in batteries for a long time as, for example, graphite anodes in lithium-ion batteries. But for many years, I've been working on so-known carbide-derived carbons. Those are like a nanoporous sponges with exact pore sizes smaller than 1 nanometer that can fit ions well. And this technology that we studied and developed has been successfully implemented by Skeleton Technologies, for example, in Europe, which has a super factory in Germany. And I just read recently in the news, they invest in 600 million euros to build another one in France. And they call it a super battery. In fact, this is a supercapacitor, but for a consumer, it's much easier to understand when one uses the word battery. And what they give these devices, very high rate and very long cycle life, like 1 million cycles, very high rate. So for application where really rate power is important, those complement conventional batteries. Starting engines operate in a wide temperature range. So those type of devices based on supercapacitor, pseudocapacitors, basically storage of ions in ports, electrostatics, are also a part of the energy storage market, providing the highest rates, fastest down to millisecond charge and discharge time, also harvesting energy from braking cars, trains, fast processes. But also lately, we have been working on carbides. Carbides are important because they use very abundant element carbon. If we complement a carbide with titanium, for example, we can again have materials that can be potentially produced in million tons that contain very common elements. What is important about two-dimensional materials like MXenes? First, we can make flexible batteries. They easily 2D materials flex. So for our wearable devices, epidermal electronics, for flexible cell phones, displays, this is what opens new technology where conventional battery materials cannot work. There is one more important thing. What does it mean, fast charging of a battery? It simply means running a high current through the battery. What happens when you run a high current through a poor conductor? Joule heating. That's why car batteries have sophisticated, expensive cooling systems, and it also means that we waste a lot of energy transforming it to heat the energy that we work so hard to produce and store. MXenes offering conductivity at least an order of magnitude higher than reducing graphene oxide can actually enable much faster charging. We make batteries that don't require current collectors. Or you can make a 1 to 2 micron film of MXene that you can produce by simply spreading colloidal solution of 2D particles on the surface and drying with mechanical strands of aluminum foil. And imagine replacing 10-15 micron metal foils with like a 2 micron MXene films. You basically shrink the battery without changing the chemistry. We can use MXenes as conductive additive and a binder at the same time because it binds stronger to oxides compared to, for example, graphene or nanotubes, and eliminate polymer binder, making also recycling of batteries easier. So basically what it means that we discover and develop new materials that can help both current battery chemistries work better, but also enable flexible, printable batteries that will be required for the future, and new technologies when batteries can be, for example, completely printed, assembled from solution without using the current processes of using metal collectors, calendaring, using polymer separators, and so on. So basically changing also battery manufacturing processes. And we are confident that those new materials will make a big difference in the future energy storage technology.
Oh, well, thank you so much, Yury. Yeah, I was just agreeing with you. So thank you so much. So thank you all, to our incredible panelists, Yury, Kang, and Shirley for joining this session today. There are definitely a lot of challenges and opportunities ahead for the next generation battery technologies. And it's clear that we have a pivotal moment that could happen in the near future. And so I'm really excited to see how things play out. So thank you, everyone, for joining this important conversation. And thank you again for our panelists. You guys have a wonderful day.
Thank you, Jay. Goodbye.
Hey, everyone. Thank you and welcome back. Thank you and welcome back. We are really excited here to have the Q&A portion of our panel discussion today. And just as a reminder, feel free to put your questions in the chat and we will answer them in the order that they come. And don't worry, if there are some questions that we don't get to, we will contact you afterwards via email. So we will still get to your questions. So I encourage you to just go ahead and put those questions into the chat. So we will go ahead and start answering your questions as they come in. I see a few have come in already. The first one is to you, Professor Shirley. So in terms of material advancements and new instruments, what material advancements and new instruments are really required to develop these next generation batteries?
Well, I think probably the buzzword nowadays, very exciting, is called the dry electrode processing. I think that has captured a lot of people's fascination. I would say that the traditional manufacturing method uses NMP, which is a toxic solvent to make the electrode. And in the new dry electrode processing methods, we utilize polymeric binders that can actually completely eliminate the solvents, which takes a lot of effort to recycle and prevent it from evaporation. And together comes with this dry process that enable the very thick electrode processing. So the area loading goes up, energy density goes up. However, then your quality control characterization become the challenge. So therefore, that leads to the development of new machines and new characterization tools to ensure how those kind of processing can lead to higher yield and the better quality of the battery. So I think from my perspective, 2025 will be the year for dry electrode processing, and a lot of the material scientists and the polymeric experts, I would say it really takes the entire community to enable a new manufacturing method, and that is the processing method is neutral to any chemistry, lithium, sodium, and even aqueous-based batteries. That I think that's an exciting directions that I would recommend people to look into.
Yeah, absolutely. Thank you, Professor Shirley. The next question that we have in the chat, it looks like for you, Kang, this one might be more appropriate. So, in terms of as you're identifying different molecules, how do you know which ones are actually useful when dealing with these electrolyte technologies? And are you using any type of like AI to help accelerate your work in that area?
That's a fantastic question. Since we are dealing with such astronomical number of molecules which are never touched or even existing in the natural occurrence, so how do we find the one that's truly useful? In this case, we are approaching this from two parallel avenues. So one is the screening. We use the based on the computation chemistry database. We use the classification model, foundational model, to quickly screen down from the based on the existing knowledge to the group of molecules which are likely to be useful. And on the basis of that, we further accelerate the property prediction using different AI models as well as computation chemistry. Those parameters could be as many as more than 20 to 30 different categories. And based on that, we further narrow down to select the molecules which are aimed at different targeted application or chemistry scenarios, such as lithium or lithium ion for fast charging, lithium ion with a silicon anode, etc. On the other hand, we also we're building the AI agent, training the large language model to build this AI scientist, which can use generative AI to build and construct the new molecules right after you feed the desired properties into this agent. And this part of the work is still under construction, and it's really showing the preliminary encouraging results. Of course, like any AI machine learning model, you need a large data set to train, to pre-train, to fine-tune, and to reiterate. And reiteration of each round is getting smarter and smarter. That's why we call them deep learning. So I hope I answered the question already. Again, first of all, we need to build this extensive and large, unprecedented large scale of the DFT database, which solves all the molecules on the quantum chemistry level. From there, we can develop further.
Yeah, absolutely. Thank you, Kang. The next question is a pretty good one as well. It's from the audience. So maybe Professor Yury, if you'd like to take a stab at it. So the question is, solid-state batteries introduce new material challenges, and one less discussed component is the current collector. So they mentioned that they've seen some articles using stainless steel and nickel and maybe some other alternatives other than copper and aluminum. Would love to get your perspective on these other alternatives in some that you've seen in your research as well.
That's a good point because most of research is focused on anode, cathode materials, electrolytes. Passive components get much less attention. One important thing to realize is that different batteries require different types of current collectors. For example, one of the advantages of sodium-ion batteries may be elimination of need for copper. When we talk about solid-state batteries, one of the challenges is how do you connect ceramic material, for example, to metal current collector? And the question is here, do we need to stick to conventional methods? Can we have a spray-coated, for example, or sputtered metal current collector on the surface that will provide better adhesion? Can we use other material systems that can make thinner current collector or more stable current collector, minimizing the corrosion? So I think that's simply the issues that need to be taken into account whenever we talk about new type of batteries. We cannot and should not just by default transfer technology and processing methods developed for the current lithium-ion batteries to this new type of batteries, because it may not necessarily be the best solution.
Yeah. Wonderful. Thank you, Yury. And then so the next question, I'll go to you, Shirley. In terms of AI, I'm curious how you're using, with the rise of AI, how are you using that for your research and that you have planned? Are you using AI and new kind of automation technology?
I would say the AI is a very useful tool that for AI for science has already been talked about previously in the the discussions we had. I just think that as we all know, AI consumes a lot of electricity, so we better find a valuable question or a few valuable questions that the AI can make contributions. At this stage, I think that the most critical barriers for doing proper AI for science is actually curating quality data. And I think Dr. Kang Zu have mentioned a few times that, in terms of computation, I think the database growth is very healthy. And we see a lot of good institutions, excellent institutions, and individual research groups are contributing to the curation of the computational database. My worry is more on the experimental side. Indeed, that science is a evolving process. The scientific data collected 50 years ago based on the imaging or X-ray, the quality is not as good as what we had obtained today. For example, with Thermo Fisher Scientific's high resolution TEM or the STEMs, we can get a new set of data. We discover new phenomena. So I think those kind of curation of the new data in the experimental side is largely lacking. And as I mentioned previously, unlike the biological and the medical field, they have a very good agreement about how to curate and maintain the database and upgrade the database. The material science field or the battery communities are still learning the process. So I'm looking forward to the next decade, how we can really build the right database or the quality database to truly enable AI for science. This step cannot be skipped because unlike the large language models that people do for, I would say, common AI, AI for science is a different game. And I certainly hope that we will play the game right so that we get information that will be new knowledge that will be truly impactful for the humanity.
Thank you, Shirley. This next question is for you, Yury. So it's regarding the grid energy storage system and the intermittency challenges that we have using renewable energy sources like solar and wind. They're not always, the sun's not always shining, the wind's not always blowing. The question is, how do you see, the carbon-based energy storage versus lithium-ion battery energy storage to address this intermittency issue?
Well, I see the question is about carbon-based thermal energy storage.
Yes, correct.
I think here. I don't recall the name of the company. I think it's something Atora or Antora that has been offering storage of energy in large carbon blocks. It's a thermal storage. Thermal storage has been considered as a way to store a large amount of energy over extended periods of time. So this is a storage for the grid. And people consider it cheap material like sand. The advantage of carbon blocks that they can go to much higher temperature. It means that they may be able to store more energy. I have not worked on this particular technology. So I think it's all a matter of economics. And as Shirley mentioned in discussion before, we need to store much more energy compared to what we do now in the future, including actually powering AI and so on. So alternative solutions for grid level storage are important, and lithium-ion batteries are probably not the most effective way of doing it here. So whenever you cannot pump water uphill, thermal storage is probably a good solution. But again, keep in mind, it only works for really large scale grid storage. Whether carbon bricks or sand or other minerals will provide the most cost-efficient solution, I think this is where proper economic calculation should be done.
Okay. Yeah. Thank you, Yury. And with that, I would just like to thank our incredible panelists for the wonderful time that you've provided in answering these questions. If there are any questions that we haven't gotten to that are in the chat, feel free to put them in there, and we will, answer them via email, as I mentioned earlier. And so, just want to thank you all again, and thank you to all the listeners. You guys have a wonderful day.